Hello, everybody. Hi, good afternoon. Um, Ready for class? Yeah. All right, cool. I have candy. I have free candy. So if you have a question, I'll throw you a free piece of candy. Your mic on. Your mic. Oh, is it not close enough? Is this better? Maybe. Oh, it is on. I don't know if it's. Hello? Is that better? Oh, I'll just wait. All right. Yeah. So if you ask questions, I want you to ask a lot of questions. You get a free piece of candy. Make sure to get probably actually. That's also nice. No, I guess I am guest lecturing today. Because Callie's at a conference. My friend Rishabh guest lectured last week. So now you get to watch me guest lecture as well. Today I'm talking about machine intelligence and data sets for high level hardware design. Um, and I stole these slides for my proposal exam. So, uh, we'll do really quick introduction. I think I'm a third year PhD student. I've been here since undergrad, since like 2018. I'm advised by Dr. Callie Howe. And then also very weird, I'm also a full-time research faculty at GTRI. So I can actually like advise my own PhD committee, which is very weird. I don't think they would actually let me do that, but it's possible. And there I work on hardware security and trust. In Callie's lab, I do other stuff. And most of my research right now is like AI for hardware design. So I don't know how many of you are actually like know what GTRI is, but essentially it's like another part of Georgia Tech that's not the school that does a lot of like research. Some of you might actually work there or know people that work there, but that's kind of like that kind of explains why there's like two different roles that I have. I just want to clarify that as well. Um, so the idea I'm going to be talking about today is that there's this like I don't know like mythical feedback loop that everyone thinks we're going to be able to achieve, where you have like chip design for AI, and then you have AI for chip design, right? So this first part is like very straightforward. We have all these applications. Um, a lot of them are AI driven, so like AI for physics and medical imaging and so on, self-driving, commercial products. And we want to design like computer chips that do this AI stuff fast or efficiently, very straightforward. Um, some of the applications we focus on, like the ones I put here, are real time or high throughput or focus on energy efficiency. And so you could use CPUs or GPUs, but I use FPGAs, and FPGAs are good if you're targeting those specific kind of metrics, right? Um, then on the other side, like on the flip side, all these like chip design companies want to use AI to design their chips. It's like using LLMs to design chips or using like reinforcement learning and other deep learning techniques, like advanced deep learning techniques to optimize specific parts of existing like chip design algorithms and so on, right? And um, a big thing that's going on now is like, is this like real? Does this translate into real improvements in the chip design? Supposedly it does, right? Based on what these companies are doing and what's been seen in academia. Um, and so the idea is that at some point we can translate like these AI model acceleration, like the hardware acceleration for the AI, to actually use for EDA design. And then on the other end, you can have like AI enhanced like chip design tools, right? So this is very straightforward. This is kind of like the big picture, like the really big picture of what these kind of companies are aiming for, what some parts of like academic fields that I'm in are focused on. And so I just wanted to give you guys that overview. Are there any questions about this general trend or topic? Remember, you get a free piece of candy. Yes, if you ask a question.
How good is AI for designing chips?
Well, it depends on what you're measuring, right? So this is very vague. This is like the vaguest possible thing you could put in the presentation, right? So if you're talking about like you get really specific, right? So like let's say you're talking about like using reinforcement learning during ASIC like detailed placement, right? They have metrics like half perimeter wire length to like measure the quality results of like that specific step and at that level. But there's like also LLMs for generating like Verilog, right? And then at that level, it's more about like, is this is the syntax correct? Like, there's like pass rates. Is the syntax correct? Is the functionality correct? So like this is very vague. You can measure how good it is, at that level of granularity. If you want to answer the vague questions, I don't know. You have to work at NVIDIA, right? They're the ones that know how much all these things contribute, like end to end, when they release like a product, right? So that's information that's really hard to assess in academia as like a single person, but in industry, that's like their whole business, right? How they're going to do that, I don't know, right? So, oh yeah, you get candy. So I'm gonna throw it at you. You have to catch it.
I'll try my best.
I hope I don't hit anybody. I'm sorry if I do. Okay. Let's see if there's any questions. Oh, cool. Right. Um, so you're taking this class because I think you're learning about high level synthesis, right? So, what is high level synthesis? Why do we focus on it? So, essentially, the way I like to view high level synthesis is it's a like a specialized kind of compiler. It translates algorithmic code, or like code that you traditionally interpret in like a CPU, um, into hardware code, right? And in this lowering process, this like special compiler, um, uh, what's it called? There's like special steps that are specific to high level synthesis that let you parallelize the algorithm, like partitioning arrays, unrolling loops, pipelining functions, and so on, right? And so that's kind of why we use high level synthesis. Specifically, it gives us a higher level of abstraction. Verilog is like not the greatest programming language ever. It has like very poor like meta programming capabilities. It's hard to like write test benches for without a lot of effort. Um, there is like system Verilog and industry improvements and stuff like that, but it's still like it's a very like, in the grand scheme of things, if you're focused on like an algorithm and then you have to drop down to the Verilog level, you're losing a lot of abstraction. So that's why using like C++, for example, with high level synthesis is very useful. It's very easy to explore different like architectural or microarchitectural choices in your design using HLS. You can quickly test functionality, and technically it's portable across devices. Like the idea of HLS is not specific to like one FPGA. It's, you could target different FPGAs or even ASIC, right? So the sell is that like you can learn it in a month, and then instead of building the accelerator over the course of a year, you can build your accelerator in the course of like 2 months or 1 month or something like this, right? So that's like the main sell of HLS. Um, Now whether you can actually do this is like kind of not true to an extent. You can learn HLS in a month, but to be really good at writing HLS that gets turned into optimized hardware code, you need to be like an expert, and that takes more than a month. That takes like 1 year of you in grad school writing HLS code, right? So that's kind of something that I'll touch on later. So high level synthesis research is like very multifaceted. At the high level, like above the actual high level synthesis tool, you have your application and your algorithms that really focus in on high level synthesis. So a lot of work is like, we have a PyTorch model. Can we lower it to FPGA using some kind of HLS, right? And there's a lot of, algorithm and application side there. Then you actually have the compiler, like the HLS compiler. That's where you get into like the compiler and PL research. Like, how do you do HLS? There's like something called scheduling and binding, all this kind of stuff. And there's a bunch of this is like every HLS compiler that I know exists, basically, is on this slide. MATLAB very weirdly has an HLS compiler. Um, and then on that side is everything that happens after your HLS tool generates RTL. So that's kind of like what you would normally expect a hardware design flow to focus on, is like taking RTL and lowering it to your device, doing physical design, so on and so forth. Right. Um, really quickly, I'm going to go over this timeline of LMs for hardware design. So this wasn't a thing before 2020. Like when I was in undergrad, this was not like this wasn't even like existed in anybody's mind. This all started basically after COVID. People using LLMs for hardware design. So on the LLM research side, we had a lot of like scaling models, making it practical. People started using like tool calling and tool feedback, using RAG and using like guided decoding to have like structured outputs. Um, we had like a lot of these early commercial and open source models. And then, closer to 2025, Now you have people focusing on like multi-agent systems, inference time scaling, like reasoning, and then now there's all sorts of new emerging open source models, right? In the LLM for hardware design community, the first thing people were doing was like, we're going to take an LLM, we're going to generate Verilog, right? That was like the very first idea that would come into somebody's head that was people were publishing about, right? And then NVIDIA came out and was like, oh, we took all our customer data, we trained the best LLM to Verilog thing ever. They didn't open source it, but they also had an eval, and then some other evals emerged. Um, and then people started using like feedback from the tools um, to like guide the LLM and fix bugs. People started also using LLMs to generate HLS code. Um, Also, people started using it for like verification stuff, debugging, actually interacting with the EDA tools. Um, and then there's like more advanced things that come along. People are like, oh, we don't have enough hardware data to do this kind of thing, generating designs hierarchically, that kind of thing, right? And then there's like a bunch of conferences and new developments. Like every EDA conference you go to now has like LLM stuff somewhere in the conference. Also, that slide is outdated. I presented that slide last year, and then since then, there's like a bunch of new stuff that has come out that has also continued to even like to push the field forward. So now, basically, um, labs are focused on post training and inference scaling. That's the idea. Is that we create all these different environments that LMs can interact with. You can think of an environment like an EDA tool or browsing the web, and they're just scaling, running the LM longer or training it longer. We have new models. We have stronger open source models that are much closer to commercial models. We have much better coding agents. Um, Now there's ways to generate synthetic data and synthetic environments to train LLMs inside of. And then also, like I mentioned, people are doing more RL on the LLMs using verifier and domain environments. I'm going to get back to what that means at a later point. And then also, since then, there's specifically been academic and industry funding interest and also conference developments specifically for LMs and hardware design as well. So that's basically in 5-6 years, this has become its own subfield. Right? Are there any questions? It's a good time for questions. You get a piece of candy. Yes.
Really?
So, that is a good question. So, normally what you do is you train an LLM, right? These big labs have a bunch of data. They train an LLM to predict like the next token based on like the corpus of text that they have, and then you can use it, right? So you can go to ChatGPT.com, type in what like solve this math problem, and it'll give you an answer, right? It turns out, um, there's two ways to make the model better. One is you do more training, right? Instead of training for 6 months, you find more data and you train for a year. The other thing that you can do is you can do more stuff after training, like when you're interacting with the model, right? So, I might ask it a math question, or like let's say you have a multiple choice question, right? And you ask the LM a multiple choice question, um, and you ask it the same question 100 times, right? If you ask it one time and you scored like how likely the answer was correct, it might be like 10%. But if you ask it the same question 100 times and then you took like the majority vote, it might be like 20% accurate. Like there might be some accuracy increase by just asking it more times, right? If you have something like an EDA tool or a compiler which tells you if the output is correct or not, then you can actually do the scaling. And so, like, let's say you generate 100 Verilog programs, and you like see if they're synthesizable. As long as one of those is synthesizable, you win one of them to work, right? So what happens is that the more programs that you generate from the same prompt when you're asking it, the higher the chance that at least one of them is correct, right? So that's what inference scaling is. Different techniques um, when you're actually using the model after training to increase the accuracy. Another thing is like using reasoning, asking the model to think out loud before it gives you the answer. That's like another inference time technique. Cool. Steps in. Any other questions? Um, so I'm going to talk about three things today. We're not going to go into in depth on like every single thing among these three things, but mainly HLS data sets for AI, benchmarking LMs for HLS design, and then stuff that is like ongoing research in our lab. Oh, and also today's attendance quiz. has a code. So you all need to go on Canvas right now if you can, or write the code down. And then you have to take the quiz to do attendance. The code is AI for HLS, AI the number 4, and then HLS all lowercase. And that's for your attendance. So I'll just also same for the people online or who are watching the recording. Everyone good? Everyone got the code? All right. The first work I'm going to talk about is HLS Factory. And this is a framework for high level synthesis data sets for machine learning and beyond. So I'm going to skip some slides. I'm not going to go into all the details here, but I want to give you the big picture of why this was our initial project and why it's focused on data sets instead of going straight into the AI stuff. And we had a lot of collaborators on this project from ASU and UT Austin. So I kind of showed you this earlier that, high level synthesis research has many like subtopics. You have the algorithm and application side, you have the actual compiler, and then you have the implementing it and running it in the real world side of things, right? And so within HLS research itself, there's a lot of like research areas. So if, like I mentioned, if you focus on the architecture, that's kind of on the higher side. If you focus on the compilers, that's on the actual tool. And then if you focus on VSLI and physical design, that's on the downstream implementation. There are some research topics that span all of this, such as like design space exploration. Like, you might have a architecture where you have a lot of different settings that you can tweak to make the hardware faster or more throughput or more energy efficient and so on. And so you have to explore all those different design points. And then also using machine learning to optimize these hardware designs. And the fundamental research that spans all of this is benchmarking and datasets. You can't do any of this stuff if you don't have high quality, benchmarks, evaluation metrics, that kind of stuff. So we need high quality and plentiful HLS data available to everybody, right? This is just pointing out some stuff like machine learning for HLS. So when you guys are going to learn more about HLS, essentially you write your little HLS program. The synthesis tool will spit out the implemented version. It'll tell you like latency in terms of like clock cycles or number of nanoseconds or something like that. And then it'll tell you how many resources you used, like how many LUTs in the FPGA did you use, how many pieces of memory in the FPGA did you use, so on and so forth, right? So one very active area of research is like, given the program that you wrote, without running the actual tool, can you predict those things? Predict, here's the code, predict how like the latency of the kernel, or here's the code, predict how many flip flops and LUTs I'm going to use, right? Another one is predicting how much power I'm going to use, and then once you train these models, you can like put them in a loop, and you can test different like changes to your code and see which parameters or configuration of your architecture leads to the fastest design or the most energy efficient design. But to do the ML stuff,
I have a question. I have a question.
less design sampled over a large space of
Yo.
HLS optimizations. So if I trained an ML model on HLS designs that just did like linear algebra and matrix multiplication, and then I gave it a new HLS design that's like something completely different, like graph processing, like the model will not generalize, right? So we have to have a lot of distinct, unique HLS designs. Also, when you run your HLS tool, there's a lot of pieces of data that appear. So you have your source code, your design space. The tool will lower it to like assembly intermediate kind of looking code called LLVMIR. It'll generate a schedule of when all the hardware operations happen. There'll be a report. You'll have the generated Verilog, and then if you go and run the actual physical design, you'll also get timing and resource usage metrics, right? So we want to collect all of this stuff. And basically, as long as I have that, I can generate everything else automatically if I do the engineering work, right? And then if I have like a design space, like all the different configurations of my design, I can like sample many different design points, all with all these pieces of data. I can generate like thousands of like data points, basically. That's kind of like what HLS Factory does. There were some existing works that tried to do this, but I'm not going to go too much into that. The idea is that people working on like HLS research, especially ML for HLS, we don't need another data set, but we need like infrastructure for people to add designs, sample new designs, generate new data points. They should be easy to add their own designs and parameterize designs. And then we want to have a lot of data and a lot of unique data. So different types of applications and kernels represented in the designs. So that's kind of like how HLS Factory works. There's like 3 stages. The design sources themselves and the design space expansion, how we generate all the different versions, then actually running it through the tools, and then aggregating the data set. So literally you run HLS Factory and you get a zip file that has like a big CSV file in it with all the like metrics for each design. And then you also get all the like artifacts like bitcode and schedule data and stuff also in that zip file. The idea is that you run HLS Factory as like a grad student with your designs or the built-in designs. You get this file and you're ready to do your research, whether it be like ML for HLS or some other kind of research. I'm going to go really quickly. So this is once you guys get more, I don't know. Have you guys talked about pragmas yet? No? Okay, cool. This is actually a good example, maybe to get introduced early. Spoiler alert. So you might have a design with a for loop, and you can actually unroll this for loop in hardware. And you tell the HLS compiler to do this using this pragma. And you can unroll the for loop in different factors, right? Factor of 4, factor of 8, factor of 16. Which one do I pick, right? So what we want to do is we want to generate different versions of the design that have different values for this, and then see how that affects the latency and resource usage and so on for every version of this design. We're going to collect all those data points, right? So essentially, this is like design parameterization, and we have this built into HLS Factory. There's like a lot of ways to do this. I'm not going to get too detailed, but essentially, as long as you have like a design space, you can generate different versions of your design. This is not DSC. We're not trying to find the best design. We're just trying to sample different points to create like a unique like distribution in our data set of different designs that have different latency and resource usage. So here there would be like 15 possible designs you could generate from source code in the design space. Yeah. So like I have a table on a slide. How do I do this in like code? So it's all automated. We have this DS like domain specific language. Like this is a configuration file that sits alongside your design. You can basically specify design space using our like syntax, and it supports like unrolling parameters, pipelining, array partitioning, which are all things that you'll learn. These are all different like pragmas that will affect how the hardware gets optimized. And then we just combine the two and we generate many versions of a single design. And then we do this for all designs that are in our built-in data set. So what kind of, HLS designs already exist out there that we built into HLS Factory? These are like the 4 major HLS benchmarks that exist. They have different kinds of kernels. Essentially, there's like 53 total from these benchmarks. And we also have like the design space, like configuration file to do the like sampling alongside all these as well. So that's cool. The next part is really boring. It's the part where you take all the designs and you run all the tools. Basically, you want to avoid like reinventing make or any build system, right? You just want to automate. Here's all my designs, call Vitis HLS, gather the files, make sure they're there. So this part's really boring. But you just run all the tools. And then there's some like structure to how we store the designs on disk. That way it's all like, we can extract the data and so on. I'm not going to get too much into this. You could read the paper if you care. And then this is all done in Python. So like we have different flows to run synthesis or implementation or get a report, and to also do the parameterization, and you can add your own. So like if you have a simulator and you want to run all your designs through like your simulator, you can add that through the Python API and run that in bulk over all the designs. This is like a really simple code snippet of how you would generate a bunch of designs using like Vitis HLS, using like the parameterization, and then collecting all those data points, and so on. And then finally, this part is also really boring. It's more engineering. We just find all the data and we put it together into like a big table and we zip it into one file. That way it's easy to share. I'm going to show you some case. So you might be like, okay, cool. You collect all this data. What can I do with this data for like HLS related stuff? So I'm going to show you some utility of the framework. So we have these 7 case studies, and then each one of these was designed and run, and like the results were collected and the figures generated in less than 4 PhD student hours, which means 1 student for 4 hours. This is mostly to demonstrate like, we have this framework. It's hard to show like what is the utility. Utility is that you can do all this research now very efficiently. One example, like I mentioned before, is that like when you run Vitis HLS from your source code, you'll get a report with like latency and number of resources you're using. And then when you run Vivado to actually implement the design in the real hardware, you'll get the real number. So the numbers that Vitis tells you are estimated. They should be correct-ish, but a lot of times they're not. But they should just be estimated. And then the Vivado will tell you the real thing. So yeah, like I mentioned, they can be different. And we actually only care about that one for like the real world. Like when our design is on the device running in the real world, that's the one that we care about. And also, if we wanted to actually collect that number, this could take, a couple minutes. This could take like an hour or several hours, right? So the idea is that we want to get that number without having to run Vivado, right? So what we can do is we can take the report from Vitis HLS, and then we can take some aggregated statistics about like the lowered intermediate like assembly or the compiler, what the compiler is generating as it lowers your design. And then we feed it to a simple like ML decision tree model, and we predict what will Vivado actually do, right? And generally, this is accurate. And the more data that we use through like our sampling, the more accurate we're able to get it. And we can even predict things like timing slack and timing violations that you can't even estimate from Vitis HLS, right? Also, we just want to show like the range of like values that we're able to cover by doing this like sampling of our data set. So if you just use the original designs, you get the green distribution, but the more sampling you do, the wider range of distribution you cover of like latency and resources that you see in your design. Here's also like a 2D like dimensionality visualization of all the different points. And you can see like different designs are covering different spaces of the design space. And then this is also broken down by individual like kernel instead of whole data sets. This is just a cool visual to illustrate. It's not super quantitative necessarily. There's also some implementation details. Like a lot of this work was just engineering, which is not like really like reviewers don't find that super cool, but it's like very valuable as grad students to have tools that are very efficient. So we did a lot of work to accelerate like the parallelism when building all these designs. We can target like Intel. Intel has their own HLS tool. So you guys are mostly using Vitis HLS. We can target both of them. We can collect data from both of them. So that's what this is showing. We can add like new designs. So part of that is that we did add new designs from like accelerators in our labs and from like educational materials. Other works also release like data sets as part of their research, but they might only like release like the statistics or the final values. And we can also integrate that alongside our data, which is what this is showing. And then finally, you can do non-ML research, which is less like popular these days, but still valuable. So for example, I have two versions of Vitis HLS, right? They can behave very differently. Like the runtime and like the final latency of my design, the research, they can vary between the versions of the tool. So can we like do statistical tests and see if there's differences? And basically that's kind of what we take the same designs, we run them through both, we gather the data, and we do this comparison. And so we can do these cool, distributions, and so that the means are different, and then do like non-parametric statistical tests to show that there is actually a difference that's not by chance. So this is just demonstrating non-ML research that is valuable, that you could still use this for. And all this is open source. So if you go to our lab website, you can find this stuff, you can run this, that kind of stuff. I guess now is a good time for questions about the HLS factory stuff. I think there's a question. Yeah.
So have you combined the design space exploration with the lighting sim? That is where, I kind of see a lot of returns for the algorithms which you're...
So the challenge there is that the way Lightning Sim works is you have to, if you change the pragmas or the source code structure or almost anything about the architecture or the design of the pragmas, if you change anything, which is what you would do through DSC, you have to resynthesize the design before you run Lightning Sim. So there's not really like, I mean, you could use Lightning Sim to get like a more accurate estimate of the latency besides what's in the report, but you still have to resynthesize the design. The one thing you don't actually have to resynthesize that you can change and get new results from Lightning Sim is like the FIFO depths. So in HLS, you can have these things called streams, which are FIFOs. You can like write to them and then read from them separately, and you can put them in like data flow processes. You have to like size these correctly, and doing that is like not trivial. So we recently published a work where we use Lightning Sim to like explore different sizes of FIFOs within your design. And actually Lightning Sim lets you like change the size recalculate the latency without having to resynthesize the design. That's the only thing that's like really that you can like change and quickly resimulate and get new numbers for. Everything else you have to like resynthesize.
But isn't it still faster than RTL-C co-simulation?
That is true. So like if you want to like, if you don't want to use the let's say you're gonna like make changes, synthesize, and then either look at the report. You could like the latency reported. You might not care about that, so you would run RTL co-simulation. You could replace that with Lightning Sim. That would make that faster. But that's just I wouldn't call that like a new idea. I would more so call that like an engineering change to make the traditional DSC faster. Yeah.
And last question is the current AI good for defining an outline for the design space exploration? Like these are bad ideas for your architecture and these are good for your architecture.
So that is research that's being explored in different ways. One of them is like, here's the design, and like you ask the LLM to suggest new values for pragmas. So you constrain it to just give me different numbers for the pragmas. In reality, what we found in general is that to make meaningful changes, like optimizations to your design, you have to change both the value, like the pragmas, like the parameters of the pragmas, and the code structure. You can't get the full optimization from HLS unless you do both. And there are people who are doing like LLM, optimize this kernel, just do whatever you want, just make sure it's functioning. I'm going to present that next, but that's like more general. More specific is using LLM to make like targeted changes and targeted ideas. Yeah. Okay. Ready? Any other questions about the data set, HLS factory? Cool. All right, I guess we'll move on. This next, I mean, this one is much cooler. I think this work is much cooler. So I'm going to talk about now benchmarking and evaluating LMs for high-level synthesis design tasks. So a lot of people love, so like the big thing right now, or the biggest subtopic that you'll find is like LM for RTL design. LM write Verilog, or LM write VHDL, or write Verilog test benches, right? If you look at like the LAD conference, most of the publications are about RTL design, and a very few of them are about HLS design, right? Over both years of the conference. So the question, very straightforward, is like, can we use LMs to do high-level synthesis design? Like, can the IHLS replace what you guys are going to learn in this class, right? So there's two things, right? Can we use the LMs to generate the designs from like a description of the design? Like, so we don't have the design, we have a description of what we want the design to do, and maybe like a test bench generate the implementation. And then the other thing is like, we have a design, and can we use the LM to like make edits to the design to make it more performant, or to generate the hardware like more optimized, right? So one of them is generation, one of them is editing. And the short answer is like not yet, kind of like a year ago. I don't know today whether you can or not. That's what we're working on right now. But a year ago, it was kind of not yet. So yeah, that was for the conference people. I already went over this. This is like the HLS flow. So we have clear benchmarking efforts on like the everything that happens after HLS. We don't really have any benchmarking on LMs for HLS, at least at that time, right? So we actually don't know much about how LMs understand HLS and can perform at different design tasks. There are some other works that existed. They were kind of bad, and like they were rushed because people wanted to like publish about it like first. That's kind of the gist, and then we built our own like full benchmarking framework, right? So the idea is that we want to make LM for HLS benchmarking accessible to everyone. That's like the number one priority of this work. This work was not to get results, but to like build the framework and software so we can run different experiments and so on. So as a result, we have all these benchmarks, we have all these tool interfaces, we have all these tasks that we can evaluate, different ways to evaluate the LMs, and then like an API, right? So the primary goal was to make the benchmarking accessible, and then as a consequence, we can like present some cool results at the end of the PowerPoint. So this is really important. So if you don't, pay attention for the rest of the PowerPoint, this is the main thing. So how does this work, right? You can ask the LM to generate an HLS design. It'll spit out source code, like C++ that will get fed into like Vitis HLS, right? So sometimes like the LM is supposed to output the source code in a way where we can like cut and paste the source code out of like the text it generates. Sometimes it can't, like it generates it all mangled and we can't do that. So that's where it could fail first. Then what we do is we try to compile the C code normally, like with a regular C++ compiler, like Clang or GCC. We just try to compile it. There's a syntax error that would fail, right? Then we try to do C simulation, which means we just compile the source code with a regular C++ compiler and then run it on our computer, like on the CPU. It's just C++ code, right? It's still going to get lowered to hardware, but it's still C++, so we can still run it. So we check whether the C simulation, the test bench, and everything is still functionally correct. And then we actually run HLS synthesis. And there's certain things in your design that could actually cause HLS synthesis to fail, which I'll get into later. And then you could also simulate it, and that could fail the equivalence checking there. And then you could run implementation of the design, and that could also fail. So there's all these places where the design can fail. Um, so to actually evaluate like an LLM generated design, the compiling part takes 10 to 30 seconds. It should take like 1 to 5 seconds, but they have terrible like template libraries, and the engineering on the tool compiler and the framework is not that good. On the Vitis side, I mean, LLVM is great. Vitis itself, like the HLS tool, takes 30 seconds to like a couple minutes, up to an hour. And then that part, like the Vivado stuff, the co-simulation could take hours. And then the same thing with the actual like implementation. We have stuff to make this faster, but still it's a challenge. For this work, we only focus on everything that happens above there. So HLS synthesis and above that. So we actually, you might ask, we should evaluate like the quality of results, like how good is the hardware that the LM is generating, like the resource usage, the latency, and so on. What we find is that like at that point in time when we did this work, the LMs were barely able to pass HLS synthesis. So we weren't going to worry about trying to also like evaluate the quality of the design and the performance of it. We just wanted to see how the validity of the design, like could it pass all these stages and still be valid? So we're not going to focus on like optimizing the design with LMs yet. So what we do is we build like 4 metrics. Can we parse? Can we compile? Can we pass the test bits? And can we synthesize? And we assign a pass at K rate to each metric. So raise your hand if you've heard of like, what pass at K means for like evaluating. Okay, very little people. So you can imagine pass at K is like if you have a binary thing that says this passes or this fails. Pass at K is the likelihood that at least, like if you generate K samples, so let's say K is 5, pass at K means at least one of those 5 is correct, right? So normally pass at 1 is a good intuitive place to start. So like the LM generates one thing. How likely is that one thing to compile? That's pass at 1. Pass at 5 is I ask the LM to generate, 5 possible outputs for the same input, like the same prompt. How likely is at least one of the 5 to pass, right? So it's much more likely that the higher K is. And we're actually going to exploit this later as like an inference scaling thing. We construct these benchmark designs also using the help of LLMs. This is like a side thing. We can take in raw HLS like source code and repositories and use LLMs to like extract the main HLS kernels and make them as like neat test bench cases. We're still kind of like working on this today as well. And also as a human, I verified all the ones that are like built into the initial benchmark. And then we also use a bunch of design sources from HLS Factory as well. This is also like stuff that like reviewers do not care about, but is like really important. Essentially, we did a lot of engineering to like parallelize everything, like parallelize calling the LMs, parallelize calling Vitis HLS, and parallelize like the synthesis and running all the tools. That way we can like hit run instead of waiting a couple hours, we get results in like 5-10 minutes. And you can see here like if we allocate 4 threads and 8 threads and 12 threads for like synthesis or inference simulation and synthesis, you can see the usage of each of these parallel pools over time. This is just a cool visualization, but we're going to use this later to like point something out. And then everything is in Python. So this is the minimal code that you need to run a benchmark, which is pretty neat. So we have these 0-shot generation and 0-shot editing flows. And right now we're working on like this tool feedback and agentic evaluation as well. And you can write your own one if you're interested in doing that. So another neat thing that we did that actually paid off is that we wrote these really nice like automations around the tools. And this seems like, really simple as like something that you wouldn't expect to be important. But it turns out now that agents are super popular, we can like plug these directly into agents and we get that for free. So we did this engineering work and we're like, oh, this is actually useful today. now that we're doing our extended work. It seems super trivial, but still kind of important. So I'm going to show you some evaluation results. So the first set of results is generation. So given a description and a test bench, generate the kernel implementation. And then we're going to have some editing tasks. For example, convert all the floating point types to fixed point types, add loop labels, refactor to use like streaming and data flow, or refactor to use loop tiling. And so all of these, we tested these open source models. Zero shot setting means like I ask the LM to do the thing, it gives me an answer, and I evaluate whether that answer is correct, and then that's it. A lot of the evaluations today are like agentic loops, or there's like feedback from the tool. We're not doing any of that. It's very simple. And then we compute the pass at 1 and pass at 5 rate for each of these tasks for every model. So here's the code generation. We just ask it to make this kernel, and it will generate it. So you'll see the pass rate, for parsing and compiling is like kind of high, but we find that a lot of the models generate things that don't pass the test bench. So the LMs can generate like valid, compilable, synthesizable designs, but they're not functionally correct. That's the main thing. For editing, this is like loop labeling. This is like the simplest editing task that you can do that doesn't change any of the functionality. You're just labeling the loops in your code. It's like very local. For some reason, one of the models is like, there's like a weird edge case, but in general, this is doable. And I imagine if you ran this with like today's model, this would be like 100%. Then there was like fixed point translation. So turning all the floating point values to fixed point values. For some reason, the models had difficulty with this, mainly because you have to change, the data type in your kernel and in the test bench and in your header file, and they all need to line up, right? So I think at the time, these open source models were struggling with that kind of refactoring task across multiple files. And then finally, the data flow refactoring is extremely interesting. So now, usually if something couldn't compile, it couldn't synthesize. Or if it could compile, it could synthesize. Now we see a mismatch. Like something could compile, but not synthesize. And that's because there's extra rules when you use like the data flow pragma that would cause synthesis to fail. So synthesis checks for these extra rules. We find that the HLS or the LMs break these rules when generating designs. And so we see more failure during synthesis. Then loop tiling, we also see failure during synthesis. The thing is, loop tiling requires a lot of correlated changes. So you have to change like loop bounds. You have to add another loop. You have to change the value in the pragma. So there's all these correlated edits you have to make. And if one of them is broken or something goes wrong, then you're not gonna, the kernel won't pass. So can we draw any conclusions? At the time, the conclusions were the open source models still struggle. And some of these tasks don't really need HLS expertise, but they were still struggling. And we just need to do more evaluation and best parts. Basically, extend the scope of the work, right? So there is a mistake that we made during the evaluation, like a really dumb one. Did anyone catch it? Anyone have an idea of what it could be? No ideas. All right, I made a mistake. So we never checked if the LM did what we asked it to do, right? The only thing we checked was the output from the LM compilable? Does it pass the test bench? Is it synthesizable? We never checked if it did any of the specific tasks that we asked it. Like, for example, I could have asked it to convert from floating point to fixed point, and it could have just emitted the same exact code and passed all those stages, right? Or same thing with the loop unrolling or the loop tiling. It could have just not done those changes and still passed every step, right? So we didn't actually check to do that, which is like kind of obvious. So is there a way to check whether the LM is doing what we ask it to do with 100% confidence in an automated way? The answer is probably not, but there are ways that people try to do this. So you can use like another LM to judge whether the LM you originally asked to do the task did the task, right? That's like one goofy way to do it. There's other ways that you could possibly go about this, but this is like an open problem, and it does like you're like, oh, the LM's not gonna just like go off and do something that you didn't ask it to do. It does matter because there's like certain things where like it could look like it changed something, but doesn't really affect the hardware. So this is an open problem that we're still working on, right? And then finally, the inference scaling thing is something I want to talk to you about. So remember earlier I said we only need one of the designs to pass, right? So I take an LM, I ask it, can you make this HLS design for me? And I ask the LLM the same question, 10 times. I get 10 different pieces of like C++ code. As long as one of those passes all 4 stages, I'm good. I can throw away the other 9. I have a working design, right? So that we're going to exploit this, right? We're going to ask the LLM to generate 100 possible implementations for like the same prompt and see like what's the likelihood that at least one of them is correct, right? Because that's all I need, right? And that probability goes up with the more samples I generate. And that's what inference scaling is. We basically get this for free because we're using like a cloud service to run our LMs. Like it's not for free if we have to run the LMs and do the inference on our side. But since we can scale it up and parallelize it in the cloud and we can parallelize all the Vitis HLS evaluation, we get this scaling kind of quote unquote for free, right? And that's what we do. We try from 1 to 30, like generate 1 sample, 2 samples, and so on, up to 30, and we see how the accuracy of at least one of those passing goes up. And this is really important. This word right here is extremely important, verifier. So in hardware design, the compiler acts like a verifier. Verifier tells you whether the LLM output is correct or not. For open-ended question answering, there doesn't exist a verifier. Like, is this conversation, cheerful? Can we verify that the LLM generated a conversation that was cheerful? It's open-ended. In this case, we just care, does the HLS code synthesize? That is checkable by the compiler. Like we don't have to, it's not open-ended, right? So we call all these tools as verifiers. And if you have a verifier, you can do this technique. Any setting where you have a verifier, you can do this, right? There are what are called weak verifiers. So for example, like I said earlier, you have like multiple choice question answer. You can't necessarily know that you can't like cheat and check whether your answer is correct while you take the test, like answer the multiple choice question, but you can do something majority voting, right? That's like a weak verifier. So there are things that are in between, like having no verifier and having like a verifier. But we're lucky in the hardware design community and in the software community, we have verifiers. We have tests, we have EDA tools, we have compilers. We should use that to our advantage, right? Essentially, we see like plus 18, plus 16% improvement, I guess, quote unquote, for free, right? So this works really easy to do. This also works for RTL design. People did not like, I did this as like a side thing, and then people did not do this for a while. And then eventually I saw like a couple papers that did this. You can get like plus 40% improvement in accuracy for generating Verilog by doing this like inference scaling. Now, obviously, today the big like commercial labs are doing this 100%, and there's way more advanced ways to do this that get you better results. But this is something that I want to point out as more generalizable than just this one project. So one of the biggest things we found was that the tool runtime is the main bottleneck, not the LLM inference. So when we like send it out and get the LLM response, that's very quick. That takes like 10 seconds. And then we have to call Vitis HLS to run like, C simulation or co-simulation, synthesis. That takes like a couple minutes. So it's kind of goofy. Like imagine you built like an LLM system that can like design hardware. It would first, call the LM. It'd take 10 seconds to reply with like the implementation, and then would call Vitis HLS, and then would just sit there for 10 minutes, right? And then finally you get like if it, errors, you can kind of go back, generate something else for 10 seconds, resynthesize, wait for 10 more minutes, right? So that's a little goofy. Like you're wasting a lot of time on the tool. So the tool runtime itself, not the LLM, is the main bottleneck, right? There's also cases where like if you have bad pragma annotations, you can like time out the tool as well. So at the conference, I presented this as like the tool feedback and agentic like usage for EDA tools is like not practical based on like these results and like just like common sense. And people got really pissed at me, and they were like, "How could you say that at an AI conference?" But this is a real problem, and it's still a real problem today. And I think more people are starting to realize this. So now there's a lot of effort to optimize EDA tools and like RL training with EDA tools in the loop, so that's as fast as possible, as high throughput as possible, right? And this is being, in general, people are focusing on optimizing these environments to scale RL training for LM. So I don't think this is that controversial, but I guess don't go to the AI conference and tell them the AI is not going to work, because they'll get really pissed at you. There are some like other ways to make the tools faster. Like you can do some like cool like Linux stuff if you're like a Linux nerd. But I won't get into that. You can also use like proxy models. So like, remember I said you could train an ML model to predict the performance of the design. So you could like generate something with an LM, and then ask like a deep learning model, like, is this design, what's the resource usage, what's the latency? You get back like an answer really quickly, and then you use that to like call the LM again without ever having to call the tool. Or we can make new HLS tools that are just better. Also, we need more designs for evaluations. Like all of these things are like heavily overfit in training data sets. We actually want to benchmark more complex things like full accelerators. Can the LM generate and edit a full accelerator? So we're doing a lot of work on this area. I'll talk about it in a second. Also, it's like not cheap. Like the reason I didn't do commercial models is because if I evaluated all these models, which were like the main ones at the time, it would have cost me $100 to present all the results in this paper. So like, I guess if you're like an AI lab and you have like a lot of funding, $100 not a big deal. But to me, it seems kind of like goofy that to evaluate all the commercial models, it's like $100 versus like all the open source models was much cheaper. There's like other details. I'm not going to talk about that. And this is all open source, right? So this is like our other work. I want to talk really quickly. I think we have. Are there any questions about that? The LLM evaluation benchmarking before I go into the last couple slides.
That companies are developing LLMs for very long.
Yes, NVIDIA has already done this, and a lot of companies have already done this.
Right. So, how will developing something for HLS, as in if you already have something for very long?
Okay. Why would you want to do that for HLS? So there's two kind of answers to that question. One of them is that when you say develop model for Verilog, do you mean like they're fine tuning the model specifically for Verilog?
Um,
Or so if you're talking about like let's say we're going to fine tune a model to be better at Verilog specifically, like what NVIDIA has done, right? I arguably think that that is only valuable for people like NVIDIA who have high quality large data sets. It's like me as a researcher, my approach is that the models are going to get better, so I can just use the models that are available. I don't need to fine tune anything specific for hardware design. As the models get better, I'll just bank on that, right? So a lot of my research is like assuming using the tools that are given to me right now, without any fine tuning, can I get good? Can I do like AI stuff for hardware design? That's one argument. But if you have that high quality data like NVIDIA, it's valuable to fine tune. Also, like if you're like Synopsys and you have like all these like technical commands and documentation that's like a large documentation, large set of technical commands, and you want to build an LLM to help somebody write scripts for Synopsys, that's another case where fine tuning might make sense. For HLS, that is a good point. Like, I don't know any companies that are so care about HLS enough where they were like, I'm going to fine tune a model for HLS specifically to make HLS like the best thing ever. Because like people don't like in industry and academia, in industry, there's less focus on HLS for the reason you described, because everything's already Verilog, right? So there's a lot of other problems about HLS that I think people focus on first before we're going to jump in and be like, we're going to fine tune LM for HLS. I personally think that all these HLS languages, they're like C++, C, and these models are good enough where you don't need to necessarily do that. Now, at the core of your question, you're asking like, why would I use HLS when I could just use Verilog? That's like a separate discussion.
Now, if I can use LLM to give me a very long code directly,
Yeah.
why would I use an LLM to get an HLS?
Oh, I guess it depends on. I mean, it's the same question of like, why would you design something in Verilog versus HLS, right? It's kind of I view it as the same question, right? So like, one reason I might generate something as HLS is because HLS has better meta programming. So I can use like template functions. I can do I don't have to worry about like if I generate the Verilog and I need to make a change later, I might have to change like the scheduling, the pipelining, all this. I can't make a simple change. But if I generate the HLS and I want to change something about the algorithm without changing too much about the architecture, I can do that. So this is like one example. But I think personally, I think that question is the same question as like, why would I use HLS when I could use Verilog? It's like or at least it's a very related question. Yeah. I would think of it kind of like in that way. Yeah. Oh, and you get a piece of candy. Awesome. Oh, you got it? All right, go. Any other questions? Yeah.
Being able to collect any insights from like industry workers that write RTO on a daily basis if they would use
I don't have that many friends. I don't know. I don't know that. Like, I guess I know. Like this is a big push in industry to bring AI to these like EDA tools. To what extent that's like successful and leading to like real productivity changes, I think at places like NVIDIA where they're taking it like seriously, I think it is, but they're not dumb. They're not just doing that. They're using AI to improve like the core of their EDA tools, not like LM is going to write Verilog. There's all sorts of other stuff that I think they're working on that I think is much more valuable. Same thing with Google. They have like the alpha chip and the place like that's not LM or whatever, but I think they understand that like LM write Verilog is not like gonna like lead to increase in performance and like productivity or whatever. But in short, I don't know. Yeah. Yes.
This is kind of on the same lines as LLM, right? Verilog in general, right? But I noticed you're like synthetic HLS designs. Have you experimented very much with synthetic RTL designs by any chance? So this is something I was working on earlier, but I think a lot of intuition gets lost. I want to see whether you knew a little more than me on that. Yeah.
So I guess I'll continue. Yeah. So one thing that we're
Scaling data basically, but yeah, go ahead.
one thing that we're working on is that we don't have enough HLS design because it's much more rare than RTL design.
Yeah.
Especially like how many HLS accelerators exist open source on the internet is like not that many. Like people don't really like to open source this stuff anyways. And so one thing is like, all right, let's have the LM write the HLS, like write something that's like for like write an ML kernel and then see what it generates 100 times. The problem is that it's very naive. Like it's not useful. It's like they'll generate like a matrix multiply, a linear layer, some vector add. Like that's not useful. So we're trying some things to like iteratively prompt the LM to like change the design in a way that makes it more complex or has more structure or has a larger design space. And so that's ongoing work that we're doing right now with the synthetic designs. We do see some improvement, but it's nothing like we're still like we're at the point where we can generate more complex design starting from like an initial kernel that it can just see generate. But generating like a full accelerator is like like the ultimate challenge. Like, can you make a realistic looking accelerator synthetically from an LLM? Just ask it to do whatever is still very hard. And it's like active research that we're working on. I don't think a lot of people are working on synthetic HLS designs generated from LLMs, but it is something that is out there like in a very small amount. Yeah. I guess you guys get candy, but I don't want to throw it that far. Let me try.
We're gonna try it like that.
I hate you.
Go through.
Are there any other questions? I have a couple of slides I want to go through. We'll do question at the end, I think. Okay. So another thing I mentioned is that we can use all this data to train these proxy models, so that way we don't have to run the tool every time the LLM proposes a new design. We can just evaluate it quickly on the spot. And then finally, a lot of this requires like boring engineering, like automate all these tools, plug the LLMs into the tools, speed up the EDA tools, use LLMs to actually make the software better, all those kind of fancy stuff, right? The end goal is that we want end-to-end agentic accelerated automation, right? So I have an application, I have a specification, a workload. I hit go, and then I get some bitstream that can run the FPGA. This is like a very naive view. Don't think that this is like the this will happen in the real world, but it's a good thing to put on a pedestal and then go reach for, right? If we can automate a lot of the steps of this process and then put a human in the loop, that's perfect, right? And then the idea is that we want this to be fast. The faster the feedback loop, you know, a prompt to bitstream in seconds, like making that like a very tight feedback loop, increases like the productivity, the design space exploration, all that kind of stuff. So that's like the ultimate goal. And it's very challenging because the prompt to bitstream right now takes like hours, right? So it's going to be a challenge. One thing that we are working on that we recently had a proposal accepted for is basically the same thing. I just want to highlight some details here. Basically, given some domain specific thing that you want to accelerate, so like medical imaging, physics, whatever, can we build some kind of system that can build you an accelerator for that application, right? And what we realize is that in our lab, like in Shark Lab, we already built a lot of tools that optimize HLS designs, interact with HLS tool, do simulation really fast, that like we can offload, like the LLM doesn't have to do DSE. Like the LLM doesn't have to say, oh, try this value, and then we try it, and then do this value, and like do that 100 times. That's not for the LLM. We know how to do that, right? We have software that does that we've developed. Same thing is like, we don't have to necessarily query the tool every time. We have proxy models. We have the Python wrapper automation around all these tools that makes it really easy. We have Lightning Sim, right? So the idea is that we're going to take all these tools from our labs that from our graduate student experience make HLS development better and plug them into this new agent research and agent design and see if that'll actually be able to generate domain specific accelerators, right? So that's kind of the current research that we're mainly focused, that I'm focusing on right now within Church. I wanted to share some resources with you because this is oh, AI, very cool. What do I do? Right. So there's two main courses I would suggest. One is this course from Stanford about self-improving AI agents. This is what I recommend you read about how people are using agents in these kind of frameworks that interact with verifiers, with environments, with tools to achieve complex tasks. Right. So I would look at that course. And then the other course I would recommend is Agentic AI for Computer System Design from Harvard. And in here, this is more of like a survey class. They talk about ML and AI for architecture, like computer architecture, like hardcore computer architecture stuff. They talk about it for physical design and lower level, EDA algorithms. And they talk about it in the sense of AI for LLMs generating hardware, automating the design flow and all that stuff. So this is more of a general survey class that I would recommend to look at the resources for. And then there's two conferences. So that are specifically if you go to any EDA conference, there's AI for hardware design stuff now, especially so it's definitely not exhaustive. Basically, DAC or any other EDA conference, you'll find this kind of stuff, even computer architecture conferences. But there's two conferences that specifically focus on AI for hardware design. One is MLCAD. MLCAD is more of AI in general, not like LLMs, but there's a lot of deep learning, graph neural networks, reinforcement learning, all this kind of stuff there. And then there's a new conference that only started 2 years ago as a workshop. Last year was the first conference version of it. And it's extreme, for a conference that's year 3, it's all the industry and community has narrated on this. So basically everyone in the EDA community who goes to all these EDA conferences came together. Was we're going to make our own conference that's just LLM for hardware design. And I would recommend you look there the past 2 years of proceedings to see what people are working on, who's working on it, that kind of thing. Yeah. And that's the end of the talk. So thank you guys. I will be around for questions for a little bit if you guys have questions. Well, that's it. Make sure you do your Canvas attendance. And then I have extra candy if you want just candy for free. Thank you.